Hi, today I want to give you an overview of the TouchGFX architecture, focusing on the MVP design pattern, model, view, presenter, and also explain how the backend system connects to it. TouchGFX uses the MVP pattern to separate the user interface logic from the hardware. This makes the system modular, organized, and easy to maintain. Each of these three layers has a specific role. Model handles the data. It is basically the brain behind our UI. View represent what the user sees on the screen, the visual interfaces and widgets. Presenter connects these two layers together. We can say it acts like a middleman between these two, model and view. The advantage of this pattern is that each part is completely independent. So if I change how I draw something on the display, I don't need to touch the sensor code or the hardware side. Let's see how data flows in the MVP system. The model receives or updates the data, for example, from the sensors or the GPIOs. Then the model notifies the presenter that the new data is available. And after that, the presenter then updates the view, which refreshes the display values. And the other way around, if the user interacts with the screen, for example, if he touches a button, the view sends that event to the presenter, and the presenter may call a function in the model to perform an action or send a command to the backend. Behind all this, there is the backend system, which I call it the real hardware. This is where we read the sensors, handle GPIOs, communicate with UART, I2C, SPI, or other peripherals. For example, if I press a physical button that is connected to a GPIO, the backend detects that and the information flows into MVP system. The backends communicate mainly with the model. The model acts as an interface between the TouchGFX UI and hardware layer. So let's say my backend reads new sensor data. The backend updates some variable. The model picks those values up. The presenter gets notified that the new data is available. Finally, the view shows the updated numbers or graphics on the display. This keeps the TouchGFX UI code clean and independent from the hardware. Once you get used to MVP pattern, you will see how powerful it is. And now that we've talked about how the MVP system works, I want to show you a real example in my project. In the project, when I press a hardware button on the board, you will see the status of it on the display. And it works the other way around too. When I touch a button on the display, it will turn on an LED on the board. So this simple example will show you the two-way communication of MVP pattern from hardware to UI and from UI back to hardware. So let's start by creating a new project. First, select your board and then choose the option that includes FreeRTOS. Give your project a name and press Create. Now we need a background image for the display. So we drag in an image widget, then select an image for it. You can also use the stock image on the left side. Just make sure the picture has the same resolution as your display. Next, we add a text widget. This is where we specify what text should appear on the screen. If we want to update the text dynamically, like changing the value at runtime, we need to use a wildcard. So we add a wildcard here and set the initial value for it. For example, we can set it to not pressed. Later in the code, we will update just this part. Assign it to a buffer, then we select the buffer size. Something like 10 is fine for now. I will explain this widget in more detail in another video. For now, I just want to show the overall flow. Let's generate the code and take a look at what TouchGFX created for us. If you open the project folder and go one step back, you will find the STM32Cube IDE folder. Open it and you will see full project in Cube IDE. These are all the files that TouchGFX generated. I'll just go through the ones that matters for this video. In application, then in the user folder under core, you can see the backend system and the main page. Inside main.c, you will find the initialization of all functions needed for TouchGFX. Notice that just before the infinite loop, the OS kernel is started, so the program never actually reaches the while loop. Now let's look at the GUI folder, which contains the model, presenter, and view pages. In the model, there is a function called tick. This function is called every frame, around 60 times per second. If what you need to read is simple, like a button or a basic GPIO in this project, and it is not time critical, you can read it directly from here. But if you are dealing with sensors or systems that require high sampling rates or more time consuming operation, then it is better to create a dedicated FreeRTOS task. So let's go step by step. Since the system is using FreeRTOS, it is better to handle hardware reading inside a FreeRTOS task. You can create this task manually in code, but I will do it through CubeMX, which is easier. Under middleware and software, find the FreeRTOS. Here you can find the tasks which are already exist in our project. The default task and TouchGFX task, along with their properties and stack sizes. So I'll add a new task. Let's call it button task. You can choose its priority depending on your project's needs. I'll keep the default stack size. You can also select external memory in the code generation option, then press OK. We also need a queue so we can pass the data between the tasks. This is one of the most reliable ways to transfer data in FreeRTOS. So we add a queue and generate the code again. Now in the FreeRTOS file you will see the new task and queue. So let's write the code for our button task. I will keep it simple. We just want to read the button in an infinite loop, get its state from the hardware pin, and then send that state into the queue using OS message queue put. Next, in our GUI system, we want to receive button status. So we go to the model. In the tick function, we check whether there is a new message in the queue. Depending on your project, this message could be a structure, but to keep things simple in this video, I'll just use a basic variable. If the model receives the value, we update another variable, something like boolean button pressed. Then based on the value we have received, we will update what the display should show. After that, the model needs to notify the presenter about the new button state, so we add a function for that. Well, don't forget to include queue definition in this file. Because we defined it in another page and we use it now in our model. And of course, we need the appropriate header files. Then we move on to presenter, where we add a function to forward the button status to the view. The presenter acts like a middleman. It keeps the view updated without directly touching any hardware logic. Next, we go to the view page. Here we implement a function that updates the text on the screen based on the button state. For example, if the button is pressed, we change the wildcard text to pressed. If not, we set it back to not pressed. Once that's placed, the system flow is complete. And now we can run the code and see how it works in practice. Now in this way, the button state is cleanly transferred from the hardware layer all the way up to the graphical interface. In the next part, I will get the data from UI and transfer it to the hardware. Alright, now we want to read an input from the user. For example, we want to detect when a toggle button is pressed. To do that, we will place a toggle button on the screen. You can find the toggle button widget right here in the component panel. Just drag it onto the canvas. Once it's on the screen, you can customize it. For example, you can pick different preset style to match your UI design. You will see the properties on the right side. This is where you can modify everything. Feel free to experiment a bit until it looks the way you want. Once the visual part is done, we need to make the button interactive. So we switch over to the interaction tab. Here we can assign what should happen when the user toggles the button. For example, we can trigger a callback function that sends the current toggle state over to the presenter. That means the moment the user taps the toggle button, the UI will notify the backend logic. The presenter will then pass the value along to the model, and from there you can do whatever you need. Maybe in this example, turn on an LED. Now we generate the code again, and then we go back into our code editor. In the screen view page, if you open viewbase.hpp, you will see there is a virtual function dedicated to the handling of this interaction. We simply copy that function into our own screen view file, so we can override it. Now we can modify the function here. So when the toggle button is pressed, we read its current state and then send that state back to the presenter. Next, in the presenter file, we need to add another function, one that receives this toggle state from the view and passes it along to the model. This keeps our communication flow consistent. Next, we can create a new function in the model so that based on the state it receives from the presenter, it can turn an LED on or off. Since I'm controlling the LED directly here, I also need to include the microcontroller header file. Once that's done, everything should compile and your LED should switch on and off based on the toggle button on the screen. As you saw in this video, we now have two-way communication working, both from hardware to UI and from UI back to hardware. I hope you found this video helpful. In the upcoming videos, we are going to dive deeper into the UI itself. I will walk you through more widgets, how to use them efficiently, and how to build more interactive screens for your application. If you found this video useful, please don't forget to like it and stay tuned. Thanks for watching.